Unit 16, Part 4. So we've just seen how to show that an argument form in sentential logic is invalid, right? An argument form in sentential logic is invalid if a counterexample exists. That is, if you can find an assignment of truth values to the sentential variables that make all the premises true and the conclusion false, that's a counterexample. If a counterexample exists, the argument is invalid. Okay, back to quantify logic now. What you have on the board here is an argument in quantify logic, and I'm going to use the model universe method to show you that this argument is invalid. Okay, this is from the exercises. You'll find this argument listed on page 311 for question 2, but remember, question 2 asks you for a whole bunch of arguments to use the model universe method, to use the natural interpretation method to show that the argument is invalid. You won't be asked to use the natural interpretation method, but then question 3 asks you to use the model universe method to show that the arguments are invalid for all the arguments listed in question 2. So it's really 3A that we'll be doing. Now, in quantify logic, now I'm teaching the main point from section 2 of Unit 16. Quantifier statements, right, range over domains, right? So to really understand the semantics for quantifier statements, that is, the truth conditions for quantifier statements, you really need to specify what domain you're talking about, right? This is kind of obvious if you think about what quantifier statements say, right? A universal statement says that a propositional function is true of all individuals. An existential statement says that the propositional function is true for at least one of the individuals. But over which domain? So I think Klenk has the example. Everything has the quantifier statement, all things have a heart. Is that it? It's true for the domain. If the domain of which you're speaking is mammals, then it's true. But if the domain you're speaking of is living beings, it is false. Not all living beings have a heart, right? So you have to specify the domain. The model universe method for proving an argument invalid begins by specifying the domain over which you're talking, right? And the only thing that matters for the model universe method is how many individuals are in your domain. So either the specification of the domain just lists the set of individuals over which we're speaking. For example, I'm using a domain of 2 individuals for a purpose, which I'll explain in time. But your specification of the domain is, I think I can get high enough, but let me specify the domain as this, AB, right? I'm going to be talking about the domain of 2 individuals. Now, validity, the understanding or definition of validity changes for arguments in quantifier logic in comparison with arguments in sentential logic, right? So arguments in quantifier logic are valid only if there are no counterexamples in any domain, right? So a particular argument in quantifier logic, right? It might be the case that if it's applied, or if the interpretation of the formulas is given for a domain of 1 individual, it might be that no counterexample is possible, right? Now, in sentential logic, if you try to find an assignment of, remember how we did in the last part, or the one before, we try to find an assignment of truth values for the sentential variables in modus ponens, and when we found that we couldn't make such an assignment that made the premises true and the conclusion false, we could then infer that the argument form is invalid, is is valid, right? You can't make that inference in quantifier logic if for a specific domain no counterexample is found, right? If you try to find so we're going to give various interpretations of, we've got quantifier statements. Those quantifier statements will take on specific interpretations in various domains, right? So I'll just lay out that part. Okay, so a universal statement, right, tells you what? It tells you everything. It tells you that the propositional function is true of every individual in the domain, right? So when you've got a domain of, say, 2 individuals, what it means to say that, in this case, we'll do this one, this premise 1 says, for every x, if x is A, then x is B, right? All A's are B's. What does that mean in the domain of 2 individuals? Okay, the whole key to these expansions or interpretations or translations is the universal quantifier becomes a conjunction and the existential quantifier becomes a disjunction, right? To say that all A's are B's is to say, when I'm speaking of a domain of 2 individuals, that if the individual A is A, then say he is B. Let's have A is Andrew, B is Betty, right? I'm saying that that is true, and that's the important bit there. Right? And also Betty. If Betty is A, B, then Betty is B. Right? Be clear again on what all these symbols mean. Capital, uppercase letters are predicate letters, lowercase letters are individual constants. So the individuals, right, our domain is 2 individuals, A and B, Andrew and Betty, right? AX means, I don't know, X is Australian, BX is, X is beautiful, say, right? So what does this say? This says, the premise says, all Australians are beautiful. So if Andrew is Australian, what does this translate to? If Andrew is Australian, then Andrew is beautiful, and if Betty is Australian, then Betty is beautiful, right? So you should convince yourself that this is the correct semantics for universal quantifiers, right? The universal quantifier translates to a conjunction saying that the propositional function is true of every individual in the domain, right? In a domain of 3 individuals, it means something different than this, right? That, and if Clarence, C, it's A, B, C. And if Clarence is Australian, then Clarence is beautiful, right? So, and big A, little c, hook, big B, little c, right? And that would be what that means. Okay, what does it mean to say that there is something that is A, right? There's something that is Australian. Well, it's to say that the truth conditions of the existential statement are in the domain there is at least one for which this propositional function is true, right? So when we have specified our domain, we can say, right, if you had a domain of 5 individuals, to say that there exists an X such that X is Australian, if you had a domain of 5 individuals, you're saying either, right? The big translation is the move from the existential quantifier to the disjunction, right? The or. To say that there is an Australian amongst these 5 individuals, to say that either this one, or this one, or this one, or this one, or this one is Australian. In a domain of 2 individuals, it translates to just, right, either Andrew is Australian or, see, always, these mistakes are very common. Big A, little b. You know what you're doing. Right? Either Andrew is Australian or Betty is Australian. Be careful when you're doing these, especially in exams and quizzes, to get the letters right. You're writing big A, little b, right? There is something which is A, so either Andrew is A or Betty is A, right? That's the correct translation of that. And to say that the conclusion is to say, for all x, bx, in the domain of two individuals, it is, so again, the universal statement becomes a conjunction, right? Always, right? I'm saying that every single one of those in the domain is B, right? So both, right? B, A, and B, B. Okay. So the crucial thing here is, once we've named a domain, and that's the beginning of your answer to the model universe method of showing that an argument is invalid, right? Once you've specified a domain, A and B, you will rewrite the quantifier statements to specify their meaning, a specific meaning for that domain, right? For a domain of two individuals, A and B, what it means to say that everything is, that all A's are X, is that two things are true. If A is, that all things are B. Sorry. To say that all A's are B is to say that to say two things are true. If A, the individual A is A, then A is B, and also, if B is A, then B is B. To say that there is something which is A is to say that either A is A or B is A. And to say that everything is B is to say that both A and B are both B. Okay, so the big move is the translation from the, once you specified a domain, you've changed form. These translations change form. That's crucial. In this change of form, from quantifier statements to truth functional statements, right? We've made it possible to do exactly what we did in the earlier part, right? Look for we can now return to truth functional reasoning, right? Because look, whereas those are in quantifier form, all of these, what form are these in? Conjunction, conjunction, disjunction, which means this is true only if both of these are true, and this is true only if both of these are true, and this is true so long as one of these are true, right? So we can do exactly the kind of thing we did in the the short truth table method, honing in on a counterexample for sentential logic, right? These are atoms, AA, AB, BA, BA, blah, 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 blah. A, B, BA, right? These are these are atoms. These are things which are true and false, right? Andrew is Australian or is not Australian. This can be true or false. So we can give an assignment of truth values to BA, BB, one more, is that it? Yeah. Right? And we can see if we can make the premises true and the conclusion false. Right, I'll continue in a moment.